You know, it's not really necessary that we have gone through Prosper and Gap and Embal in this course, because with Excel we really can show how you perform the calculations, the fundamentals, what you have to do in every time step, flow equilibrium. But I thought it's nice that you have some exposure very early to some tools that you're going to be exposed in the future, and uh, and also you know that you practice. So that's why we invested like 1 week almost in that. Yeah, I'm not planning to evaluate that in the exam. You won't have an exercise using Prosper and Gap because we have so few licenses. We also have some master students and project students that they are working with these licenses, so it will constrain even more, you know, the time frame that you have for the exercise. But I just want to take with you, so some things, because it's not good all the time to be married completely or to be locked with one particular simulator, okay? Because you know, you change company or you change your company, maybe in the future gets a better offer from another vendor, from another company, and they might switch and use another software. So what I think is important is that you know the fundamentals, you know what is needed, and where to put it in the software is a different issue. Okay, you can all the time click and try to navigate through the software for each particular, each vendor will have the way that they arrange things are different, the way you find things are different, the models that they offer are different. So if you know the basics and the fundamentals, and you know where I'm doing the equilibrium, what does it mean, what kind of information I should input, you should be in really good shape to tackle, to be able to use with some training any type of simulator. So I think that's what I want you to take with you, just the power to be a smart user of a simulator. With Excel, the beauty of it is that you can go behind, we can do just very simple cases, but we can go behind and we can see exactly what you have behind. In commercial simulators, you don't have that facility, and we understand, you know, the software companies, they want to protect their interest, okay, and their asset, their intellectual asset is really in the code. But you have to find ways to quality control what you are obtaining back. Okay, if it makes sense, does the rate make sense? Does the pressure, do the pressure make sense? Okay, so all the time, just some comments is just quality control, input and results of the simulator, always, okay? And not only once, but you maybe 3 4 times you go through the input, exactly what does it need, and especially this input that you really don't know how it is using it. Okay, maybe you're doing material balance and it's asking some information about platform, so you say, why do you need platform? I'm just representing the reservoir. And if you go maybe read through the manual, you say, in case you don't have gap or you don't have prosper, you can do simulation just using the tank. Okay, it's a functionality they put for someone that didn't have anything else. So QC always, and for that it's very important all of this qualitative behavior. Okay, like I told you, the available pressure curve should look like that, required pressure curve should look like that, and for example, multi-phase flow, what happens when you increase GOR? Okay, what will happen with the equilibrium point? Does it go like that or does it go like that? Okay, things that allow you to try to quality control qualitatively, because you won't be really to make it quantitative, but qualitatively how the system should what happens when you increase. So here, which one has higher wellhead pressure? Okay, that's bottom hole pressure versus Q. So which one of these has highest wellhead pressure? 1, okay, is higher than 2, is higher than 3. Why? Just because when the pressure, the back pressure is higher, I should be producing less rate. Then another thing, so remember that garbage, what you call garbage in, gives you garbage out. Okay, so all the time, just also quality control not only the way you put the input, but also the information that you have. And you see you have different sources. That input information comes. Some we need some PVT model. Usually that we get in production. We get it from reservoir engineers. We need some layout, well layout of the system. Okay, and here we have of the production system, or we can call it the production network. Okay, and that, for example, we can get it from the subsea department, and the information about the reservoir, we get it from the reservoir analyst engineer. The information about the well, we get it from the drilling and completion engineer. So you get it from, and the for example, the productivity, you get it from the well test engineer. Okay. So you see, you are trying to merge many different sources, because you need all of these elements to make your models. And models are extremely useful, even if they don't give you the right result. Maybe the right result is here, but if it deviates, it tells you maybe there is something strange in your system. Maybe the tubing size is a bit smaller. Maybe the fluid that you're circulating is different. And if it matches very close, then you can use it like a surrogate. You can say, that's my real system. Now what happens if I change these and these parameters? How much will I get? Okay, so it's very useful to have a virtual system. It can help you to understand your real system, can help you to run sensitivity analysis and then apply the changes in the real model, or it can help you to understand why you have some difference, okay, to make troubleshooting. But for that you need to kind of combine different input from different places, and that's very challenging, and to quality control that information takes a lot of time. But you will be rewarded after you have a very nice model at the end. And also take into account that this might change with time. Okay, the fluids that you produce change with time. Maybe the network changes. They found some new information about the reservoir, so they have to be updated all the time. And that's one of the challenges that we have when we say integrated in IAM, integrated asset modeling. Okay, when we try to integrate models. Okay, so now let's just to refresh your mind. We were, long time ago, last Tuesday was it, I think, we had an example in class. We were making an exercise in class that just to I told you how to perform pressure drop calculations in a pipe, in any conduit. Okay, can be a pipeline, can be a vertical pipe, can be a rise or anything, steady state. And I told you, you start from a known point with pressure and temperature, you assume a rate, and then you progress. You say first, the standard rates I convert to local conditions. If I have a compositional model, I told you, please first calculate the total mass rate, then you use the EOS to calculate the mole fraction, or the mass fraction of the oil and the gas, and then you calculate the local rates, and with the local rates you calculate the superficial velocities. With black oil, it's more straightforward. You just use that matrix to convert from standard to local, and after that, with this and the fluid properties and the pipe properties, you go to your multiphase expert to say, give me dpdz, okay, give me the pressure gradient, that this will have the three components, acceleration, friction, and hydrostatic. And then you have to integrate, so you have like 3 steps: fluid properties, the multiphase expert, and then you need the integration. Okay, and there are many different ways to integrate, some of them explicit, implicit, each software depends slightly what they use, but I told you here is like assuming that the pressure in the next point, you're going to calculate it as the pressure in the previous point times delta L and the derivative. Okay. So I said, well, let's make a class exercise, and the class exercise is just a vertical well of 2.5 kilometers depth. So it's, let me just refresh that maybe. Okay, and we took a case that we said we have one well. This is a huge tubing, huh? Then you have, actually make it much smaller. Okay, you have the formation, and here you have certain pressure and temperature, and we have certain rate that we assume that is circulating through here, and that depth is to 2500 meters. And we are going to go above. We want to calculate, I think the initial division that we made was every 500 meters, so we will have just roughly 4 points, right? So one here, 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 and here, right? 2000, maybe a bit. So many, I think we did change it a bit. Yeah, every 1500 points. Well, no, I think it's we use a mesh that is not exactly regular, but it jumps to 1000, then jumps to 500, and then goes to 0. That's not very common, okay? Usually we use regular mesh, but okay, for the sake of the exercise. So we are departing from that point, Q and pressure and temperature, and we want to calculate what will be the pressure in all the other points in the tubing. And the values that are given are standard oil and gas rate, bottom hole pressure, reservoir temperature, internal diameter of the tubing, the true vertical depth, and the wellhead temperature. Okay, that gives you already the gradient. As I explained in class, that procedure is for pressure only. If you have temperature, you have to either use another equation or you have to assume that you have already a temperature profile. So in that case, we are assuming that the temperature here will be 60 and the temperature here will be 70, and we can assume just a straight line. Just any point in the middle you can interpolate and you can find right away what will be the temperature at 500 meters and the temperature at 1000 meters. If not, you have to use a temperature model that I hope we can do some exercise later with HYSYS when we talk about flow assurance. And the specific gravity of the oil density at standard conditions and the specific gravity of the gas density at standard conditions. Well, that's actually the density at standard conditions. And you have the composition. So for that we were using a free HYSYS, a free simulator that we are going to use just like our property generator. So we said, if you remember, we just add the composition here, right? We add the conditions at the bottom hole, and that's what we obtain. We obtain that is initially is pure liquid, because the mass fraction and the mole fraction of liquid is okay, of liquid is 1, and if we plot the phase envelope, we got that, and the point is just outside. Okay, it hasn't met yet the bubble point. So what we left so far is we said all of the mass flow, the total mass flow is oil, and there is no gas at that particular point. So then we have to calculate the local rates. Okay, why do we need local rates? To calculate superficial velocities. If you remember, superficial velocities is the volumetric rate divided by the cross-section area of the pipe. So let's see what are these densities. The density of the oil is, we go to phase property, liquid. Density of the oil is should be someplace here. If you see it, just density here, 500. Okay, so I copy, paste here. The gas, I don't need it because I have no gas at that point. So the rate of the oil will be the mass rate divided by the density of the oil, and the gas will just be 0. Superficial velocity of the oil is the rate of the oil divided by the area, and the area, maybe we can calculate it here and leave it just cross section. Okay, that will be that's the diameter squared times pi times 0.25, right? The cross-section area of the pipe. Here we don't care about hold up, anything. It's just superficial velocity. Remember, you divide across the full area, the cross-section area. This is the real velocity that you need to have the hold up. Okay, so then we say Q oil, superficial velocity of the oil will be that number divided by the area, and we log the area because it should be okay, and it gives me 2.1 and 0. Just liquid. At this point, you can just use your Bernoulli equation to calculate pressure drop, right? You don't need any multiphase expert. You can use, if you remember your course, maybe they gave it in kindergarten. They say that if it's purely liquid, you can say that H, the energy in 1, is equal to the energy in 2 points, right? And then you say the energy in 1 is P1 divided by rho 1 G plus the elevation of 1 plus B1 squared over 2G, and P2 but you have to add the losses, right? If I'm flowing from 1 to 2, I have to say I have some frictional losses, and the frictional losses are usually F, the friction factor, times L divided by the diameter, B squared over 2G, right? You remember that equation? Long time ago? Barnehage, kindergarten, no? Yeah? Well, that you should know from before, okay? That's Bernoulli equation for incompressible, Bernoulli conservation equation. That's for incompressible fluid. Okay, and then I say really it's not ideal because I have some losses between 1 and 2, and these losses I can represent by, for example, if it's just a pipe section, you can represent them like that, but if you have a valve, for example, then you can represent it with K, a factor K divided by 2 over G, if it's due to accessories. Okay, I guess that sounds familiar to you, more or less, no? From a long, long time ago, in a galaxy far, far away. Okay, so but we are lazy. We are going to use our multiphase expert, even if it's not really multiphase. We're going to say, please tell me this dpdx. So let's go to our multiphase expert, that we should have him or her someplace here. Okay, so first we need the viscosity of the oil, viscosity of the gas. Okay, that really, if it's single phase, we don't care too much. Let's put first the superficial velocity of the liquid, 2.111. Then this will be 0. And the angle from the horizontal of the pipe, so that the angle is exactly 90 degrees, and it should be in radians. So you have to convert from radians to degrees. Diameter, it's what was the diameter? 1, 2. Okay, so let's change that. I think no, it's exactly that. And the roughness is I don't have the roughness, but with the roughness we use the same value that we had here. So these values are all okay. Now I need the density of the oil, that is 500.53, and the viscosity of the oil, that I can also take it from this guy. So the viscosity of the oil is dynamic viscosity, okay, 202 to the -4. And how much is that in centipoise? I think here we need it in centipoise. No, in Pascal per second. Okay, so it should be just copy and paste. Okay, that clear? I don't need to fill anything for gas, because gas doesn't play any role here, just the oil. And we obtain a dpdx of 5028.53, and we are in liquid, which is, we knew it already. And paste, okay. Now to calculate the P, remember we are going from bottom up. So we say that P is equal to the previous P plus delta L, okay, that is this number, sorry, this number minus this number, okay, multiplied, it should be minus here, times this number. That correct? Yeah, we have a pressure drop from the bottom to the next section, so that's why we have the minus. And then we say we have just the length of the pipe section, which is 1500 meter. Okay, and that gave me actually a huge, let me just copy that and put it there. Oh yeah, I have, this is in bar and this is in Pascal, right? I think this is giving me in Pascal per meter. So I have to divide that by how much? 10 to the 5. Okay. And temperature, remember I have to interpolate, so one way to interpolate is just linear interpolation. Yeah, so it will be the temperature here plus the slope, right? And the slope is 60 minus 70. Let's just calculate maybe here thermal gradient, and that's in Celsius per meter, and that will be the temperature at the top, or the temperature at the bottom minus the temperature of the top, divided by the elevation minus 0. Okay, that correct? Yes. Okay, so now I say that temperature will be this temperature minus the gradient times this one minus this one, this one minus this one. Have to, because of, you know, sometimes that happens because one is lazy, you have to do everything. Okay, so that's TBD. So you have initially at 2 500, and here you want to know it at, you have it at 0, so that's 60, and that's 70. Okay, and you want to know it exactly at, how much was it? 1000, right? So you're saying that 70 minus 60 divided by minus 0 is equal to 70 minus the temperature divided by minus 1000, right? And then we clear up, and then we say that number we already have it, that number we don't have it. The temperature will be equal to 70 minus, or it actually it's yeah, it's minus, right? Minus that number times, yeah, by that number. Okay, 64, and that should be not in, but should be in blue because we calculate. And now we have, again, that's the next point in the tubing. And what do we have to do now? Go to our expert and see if we are going to be inside or outside the dome. So we can go inspect it here because it will have the same composition, right? It's going through the same tubing. So why it should change composition? The mass should be conserved. So we have 64. 64 is someplace here, and 64 is someplace here, and 130 something. So we might be still outside. We still might be in liquid. So let's do that very quickly. 139. And 64. Okay, I'm still in liquid. Okay, so I copy it very quickly. Liquid fraction 1. This is just the same as before. And I wanted to show you some multiphase, and it's not refusing to change phase. Let's hope that for the next step. Density, no gas, and the Q rate of the, this should be these two, 0, and okay, it reduces slightly, superficial velocity. And what we need now for our multiphase expert is, well, in this case it's single phase expert. We are overutilizing his capacity. 513 was the density, right? And we need the viscosity, that will be 215. Okay, 5148, and we have to paste it. Okay, and that divided by 10 e to the 5. Okay, give me a slightly, no, that's because of the decimal. Very similar to the previous, and now I just drop that down. I think it should work, right? And 137, and it should, I think it's still in, but why so? Does that make sense? These units are in Pascal. So let's do some quality control on the. Here we say we have 1500 meters. So how many bars is that? So we say we had just a loss of how much? Of this number minus this number. 8 bars. How much is it if we just consider a column, hydrostatic column of water? A hydrostatic column of water of 1500 meter, how many bars is it? Huh? 15? Yep. All of you saw that? One column of water. Imagine one column of water of 15. Okay, and the density of the water is. Okay, and then you say that how do we convert to pressure? Is 15 times 1000 times 9.81. Okay, that is approximately 10. So we get 15, 0, 1, 2, 3, 1. And then to convert to var, we divide by 5. 1, 2, 3, 4, 5. But we made a mistake. What mistake do we have? 1, 2, 3, 4, 5.
Isn't it 1 bar every 10th meter? So it's right.
Yeah, but we are just converting. It should be 150 bar.
Yeah.
Right?
Yeah.
Okay. So this value that we're getting of 8, it's a bit too small for 1500 meters. Hmm? Of course, the density is not how much is the density of the gas? Might be something between the density of the gas. Yes, any sort of problem? Anyone?
You only include the friction, I think, and not the gravity loss.
Yeah, but this is just to a simple quality control. Okay, if there is no friction, no movement, everything is static, you should get with water 150 bar. I think this calculation is correct, right?
Yeah, that's correct.
Okay, so gravitational acceleration times the density times that. So that gives you 150 bar pressure drop. Now, if the gas usually has, like gas, for example, air. Now here, this air, what is the density of this air? Like 1, right? Kilogram per cubic meter. But the compressed air usually is something between 50 and 200. Okay, so it's like that divided by 5. Okay, so how much do we have there? 30 bar. Okay, but we are talking about liquid also, so it should be closer to this number, 250. So why are we getting so little?
You've only included friction in the dpdx. You need to include also gravity.
In this DP?
Yeah.
No, but that DP is everything. My expert gave me is.
Do you have depth in your other sheet?
Hmm?
Have you included the depth in the other sheet?
No, but that's just that's you find it at that particular point, and then you integrate. So the integration, we're doing it here. Okay, that's the integration, but maybe there is something wrong here.
Yeah, but you need to add the density times the height times the.
No, that this DP has everything. This DP has the acceleration, density, and friction. It's supposed to have everything.
I think you have one more zero in your calculation.
Maybe this is kilopascal. Maybe that's the reason. But very strange that we didn't catch that error last year. Five. Yeah, now the professor is in trouble. Bar, and that's divided by 1 e to the 5. Oh, okay.
Yeah.
So that was the reason. Okay, it was 10 e to the 5 was, 1 0 extra. Okay. Yeah, no, you have to do some quality control. I didn't do it, okay? I was trusting in the model right away, and then I got exactly what I told you not to do at the beginning of this hour. You have to quality control, okay? So now it gives me how much? 75 bar, and pure water is supposed to give you 150, okay? So you say the density is like half. It makes sense, okay? With plus friction, plus acceleration, etc. But that number contains everything. This dpdx contains all the three components. Yes, and then we come back. So here this was wrong. Okay, 72 and 64. Probably we are inside the envelope. Okay, 70 something. Okay, we are going to be someplace here. And the temperature. So we're going to be exactly very much inside the envelope. So let's change that. Make a small correction. 72, 64. Let's see. Liquid. Okay. The mass fraction of the liquid is 0.93. That means the amount of the mass flow of the liquid divided by the total mass flow. Okay, 0.93. So let's use that to calculate liquid mass fraction. Then the mass flow of the oil will be just this number. Sorry, this number. The total mass flow, I block it, times this fraction, right? And then the gas will be just the difference. Just that number blocked minus this number. Okay, 0.8, very small amount of gas. Density of the oil, let's see what is the density of the liquid. It's 578. So it became heavier. Why? Because it's releasing gas. Okay, so the lights component are escaping, and so it's becoming heavier and heavier. The density of the gas is, so I go here, vapor. Density of the gas is 52, as I told you. Then Q oil will be just divided those two. Q gas will be dividing just those two. Superficial velocity of the oil, superficial velocity of the gas. Okay. And if you see, even though there is a very small amount of gas, already it has a significant velocity, it has a significant superficial velocity. So now we can go to our multiphase expert to, to fill all the information. So we say the velocity is 1.703, 1.34. Then this remains the same, and now the density of the oil is 578.4. The density of the gas is 52.85. And now I need these things from my calculator. So one of them is the viscosity of the oil or the vapor. This should be at the end. Viscosity of the liquid. Oh, sorry, they should be, I paste them opposite or not. Okay, and then the surface tension is here. 0. I have to check that it has the right units. Yes, paste. Okay, and you see slug pattern, slug flow, that means intermittent, and I have 3.223. Go back, paste here. Okay, and now what happened here? Oh, that should be divided again by 1 e to the 5. Okay, 55. So you see, it's a lot of effort. You have to contact the expert, and that, if you have too many subdivisions, it becomes a heavy process. So that's why sometimes it's more practical to have them in tables. Hmm? But you got the idea. Yes, so before we close, there was one comment I got during the break about exercise 3, set 3. This one, okay, about this problem of these two reservoirs, Abu Hadria and Khurasania. That you were, I told you that you have to maximize plateau. Okay, you have to be sure that the plateau will be maximum for the full field, but also that it will fulfill the API restriction. Okay, the API. If you go back to our in the classes, if you go back, I think it's maybe 2 weeks ago or something. We have done the discussion. Okay, I told you that what happens if is this page 114. So you want to make that the two fields enter into the client at the same time, and there is only one unique value, plateau rate, for both fields, right? So what I suggest to solve it, I will suggest first find that splitting, find that value, okay, that you're going getting that question anyhow. That question, it says if is it where is it if the API is not an issue, 3, okay. So you have to do that anyhow. So I will suggest doing that and calculating the API that you get from the field and see if it's below or above the required. Okay, if it's below, you have one option. You can take it almost, if it's below, you can take it, increase the production from the light reservoir just until you get the right API. Okay, because you will get probably that you will produce more from Khurasania than Abu Hadria, right? But you won't get the API. So you produce less, start to reduce from Khurasania until you get exactly the API. And that's really the place where you maximize, when you cannot do anything else, okay? So in that case, the API is prohibiting you from having the maximum plateau length that you can have, okay? So you use it like a lower bound. Now you can get creative if you want, or you can try. There was a student last year that he said if you don't produce in plateau both of them, but if you produce both of them changing, you can even increase further the plateau still honoring the API. But that's only if you have free time, you're bored on the weekend or something. But he had a very nice way that he said, well, they won't be constant, they will be changing, increasing or decreasing. And that way he managed to prolong a bit more the plateau. But in this case, we are restricted to say the two rates from the two fields are constant. Okay, in that case, really, you cannot honor the two things at the same time. You can either honor that the plateau will be maximized or the API will be exactly that value. Okay, and you have to know which one has priority in this case. So what I would suggest, first solve task 3, see what is the splitting that you need, check the API, and then start changing the splitting until you honor the API on the plateau period. Okay, any question before we close? So summary for today: GAP, Prosper, and Embed, a bunch of information in one. I tried to leave you to do it so you can get some expertise. And then we talked about this example that we had missing, and yeah. So for next week we will talk about pumping, okay? It is artificial lift pumping and multiphase boosting. So see you next next Thursday, not next week. We are only Tuesday. See you.